this demonstration, I'll set up a transient blade row analysis using the Fourier transformation method as part of blade flutter modeling. This is the full geometry of the rotor I'll be modeling. The machine is rotating at 1800 radians per second and contains 36 blades. I'll use the Fourier transformation method and model only 2 passages. The blade vibration is modeled as forced periodic motion at a fixed frequency with a specified nodal diameter, 4 in this case. In CFX Turbo mode, I can easily duplicate a single passage within CFX Pre. I have specified the speed in the mesh file. Now all I have to do is expand the passages and alignment section and click Edit. I'll change the passages to model to 2 and click Preview. It looks good, so I'll click Done. I've applied a total pressure profile at the inlet. More detail on how to apply a profile boundary condition is shown in tutorial 37 of the CFX documentation. I'm also using a static pressure outlet of 138 kPa, utilizing radial equilibrium pressure averaging. I have solved the steady state case. I will use this to initialize the transient case, which will utilize the Fourier transformation method. I'll start with the steady state case and make the modifications I need to run the transient analysis. The first thing I need to do is change the analysis type to transient blade row. I need to enable mesh motion for transient blade flutter calculations. I do this in the domain by choosing regions of motion specified under mesh deformation. I need to expand the panel because I want to use a custom CEL expression for mesh stiffness. This will cause some errors to appear because there is no mesh motion specified at any boundary. I can fix this by right-clicking and selecting Auto Fix All. I'll ensure the proper mesh motion is specified as I complete the setup. A modal analysis on the single blade was already done using ansys mechanical and exported. You can see here that the values for vibration frequency and maximum periodic displacement have been automatically entered into the dataset for this simulation. Each section corresponds to a passage of the 36 blades in the rotor. This last column shows the passage number. I'll initialize the blade data so I can use it in this simulation. To display the profile, I'll select this visibility option. This will ensure the profile is correctly aligned with the blade surface. I'll edit the R1 blade boundary to use this profile. Select Mode 1 for the profile and click Generate Values. This will now apply the profile that was read into the boundary condition. Values are populated automatically. I'll manually specify the scaling factor. I want the maximum displacement to be 0.0015 meters. By dividing the desired maximum displacement by the maximum displacement in the mode shape, we get the intended shape. I'll also enter the desired phase angle multiplier, which is 4. On the left is a phase angle multiplier of 2, and on the right is a phase angle multiplier of 4. This gives an idea of the case we are modeling. The deformation is repeated periodically around the rotor according to the phase angle multiplier. I need to modify the shroud boundary to use the surface of revolution mesh motion option. The Fourier transformation method requires an interface between the 2 passages called the sampling plane. I'll call it R1 sampling plane. This interface will be used by the Fourier transformation method to collect information about the flow. The data will then be transferred back to the rotational periodic boundaries with the proper time shift. I've chosen the regions I need. You can see it is between the 2 passages. I also need to make this a GGI interface. Fourier transformation periodic boundary condition mappings are affected by the mesh motion applied to the periodic interfaces. You can prevent this by changing the mesh motion options for the periodic and sampling interfaces to stationary. Now I can set up the transient blade row model. I'll be using the Fourier transformation model, and I'll be performing a blade flutter calculation. For the transient details, I'll use a time period value of 1 over the mode frequency of the blade. For the time steps per period, I need to do a quick calculation. Phase angle multiplier is 4, and therefore the interblade phase angle is 40 degrees. We want to set the number of time steps to be some integer value multiplied by 360 degrees divided by 40 degrees equals 9. 72 is an integer value of 9. 72 is also convenient since it is twice the number of blades. The periods per run I will set to 10. I'll create monitor points for aerodynamic damping. This is the most important result for this simulation. The aerodynamic damping monitoring is built in and it integrates the work done by the fluid on the blade over one period. I'll create 3 points. Now I can run the transient case. I'll run it until the periodic nature of the problem is observed. After 700 plus iterations, I'm confident the solution has converged and I can begin looking at other variables. Firstly, I will look at the aerodynamic damping. I can see that the values remain positive after the case converged. This ensures that the vibration is damped for the frequency being studied. I'll insert a contour and color it by average wall power density. If the blade was not correctly damped, the average wall power density could provide insight to areas of the blade that are not correctly damped for potential redesign. And this concludes this demonstration of blade flutter modeling using the Fourier transformation method.